Oh, okay, awesome. It's working now. Yeah. Okay, let's get started. So let me just set up my OneNote. This will be where I'll just start my camera. It looks like we're just gonna have to go without my face. That's okay. Okay, chuck this over here, and let's get started. So yeah, today we'll be just talking about Math2521 and 2621 complex analysis, and hopefully I guess this revision provides a bit more support for those doing this course this term. So we'll just go over some basic concepts at the very beginning. So yeah, so this table of contents. So intro to complex analysis. We'll start off with some basic knowledge, right? So obviously a complex number is a number that can be written in two forms, or at least two forms. The first being Cartesian form, so z equals to x plus iy, where x and y are sort of the coordinates, right? And then there's another form which is Euler form, where it's basically written as z equals to re to the power of I theta, where r is the radius, like the size of the complex number, right? And theta is the angle between the horizontal axis, so the x-axis, and the complex number. And just like I guess numbers in the real number field, addition, multiplication, and subtraction still hold. And I guess division still holds, but when we try to divide two complex numbers, we usually prefer for the denominator to be purely real. So the I guess method to how we get that is by multiplying the numerator and the denominator by the conjugate of the denominator, so that we can get the denominator to be fully real. And I guess another important point is that complex numbers, because they have, I guess, a size and an angle, they can also be represented as vectors. And when you have something in like Euler form, where it has a size and an angle, you can also scale and rotate complex numbers about the origin. And I guess just to finish off the basic ideas and rules and ideas, we also have that the size of a complex number squared is equal to the complex number multiplied by its conjugate. And another important idea which will come later is the principal argument, which basically limits the angle that we see in Euler form between minus pi and pi, where it's inclusive of pi, but not minus pi. Okay. And I guess other basic stuff that we need to cover is the triangle inequality, as you can see here, and the circle inequality. This basically just says that the modulus of, I guess, the size of the differences between two complex numbers is less than, I guess, the difference of the two complex numbers exactly. Okay. And now we're just going to dive into some more complex analysis specific stuff. Okay. So this is topology and sets. So let's just first talk about an interior point. And so there's this definition here. There exists an epsilon larger than 0 such that the ball containing the ball centered at x with a radius of epsilon is included within the set, where the ball is an open ball about x or radius epsilon. So what does that look like? Well, I'll give you an example. So if we draw say the set here, right? Actually, it might be better to. Actually, no, we'll just do this. Okay. If we do this here, right, and let's place a ball, say over here, within the set, right, like over here. where this is its center x, and its radius is epsilon. Well, this is an interior point because for every because we're able to find an epsilon, right? Basically this epsilon right here, such that everything inside I'll use a different color. Everything inside this ball is also included within the set S, which I will label. Right. And that's basically the definition of an interior point. Pretty simple. And then an exterior point is like basically the opposite, where we have say a point over here, where this is a different x, let's call it x1, and it has a radius of say epsilon 2, where we can find an epsilon, so in this case epsilon 2, where everything inside the ball is actually not included within the set, right? Another way of expressing this is that the intersection of the set with the ball is just an empty set. And now if we sort of like consider the other case, which is a boundary point, so say something like over here on the boundary, we can see that we have both points that are within the set as well as points that are not within the set. And so that's basically the definition of a boundary point. But these are just more, I guess, formal definitions. Yeah. And we can extend this to, I guess, further definitions. So a set is considered a open set if every single point within the set is an interior point. So what that would look like is, I guess, something like this. It's usually denoted by dotted lines because all these, basically, if we were to have these boundary points, right, there would be boundary points and we can't like classify them as interior points. So that's why this set over here is open, because every point within the set, so like over here and like over here, we're able to find an epsilon that basically creates a ball that has all of its points within the set. And so this would be an example of an open set. Let me just double check that. Okay, awesome. Yeah, and then we have a closed set, right, which is basically the opposite of an open set. You can think of it like that. Well, more formally, it's if the complement of S is open. So I guess the complement of this set, this open set. Actually, no, we'll draw a new one. So it's something like this. S. The complement of, I guess, this set S is everything that's on the outside, like here, as well as like this dotted line that doesn't include these boundary points here. And because this set is open, because all of these points are interior points, that means the set S must be closed. And then we have a closure. So the set of all points in S plus all of its boundary points. So that's just saying like, okay, if we have this open set and we add its boundary points, I'll denote it by red, the red color, like this. Then basically if we have red plus the white here, that's the closure. Okay. Hope that's straightforward. Yeah, and then I guess bounded is pretty self-explanatory. Basically, if we are able to basically just chuck everything, I would draw a new set. So like this. If we're able to chuck everything from this set inside a larger set, say this red here, like a ball, we can say that this is bounded, right? I guess more I guess a nicer way to think about it is thinking about what is not a bounded set. Well, if we had this green set S, right? If we looked at its complement, which is like this blue here, it's not actually bounded, right? Because it's basically the whole complex plane minus the set S. And so this would be unbounded. Yeah. And then we have compact, which is basically closed and bounded. And region, which is basically like an open set with none, some, or all of its boundary points. I guess a good example of a set that is not a region is, say, a line, right? Because a line only consists of boundary points, right? It doesn't actually have with properties of an open set because it doesn't have any interior points. And so that's why a line wouldn't be considered a region. Yeah. And then let's look at arcs. So a polygonal connected path is one where if you have a set, like, let's use white, like this. A polygonal path is basically like, if you have one point and another point, you can connect it using just one line. And a polygonally connected path is one where you use multiple lines, where this end of this line segment here is the start of a new line segment. It's like this, right? And so I guess an example of where it's a set is not polygonally connected is when you have, I guess, two separate sets, right? You can't really connect a point in here and a point with here, right? Because if you do, then, I mean, these points aren't within the actual set, okay? Yeah. And then we have a closed path. If basically like the end of the last point, the last line segment is connected to the start. So something like this, right? That's pretty bad, but I'll add another one here. And it's like this. Yeah. Okay, so what else is there? There's also a simple, right? The simple property. Nope, wrong one. Maybe here. The simple property, which basically just says that this path doesn't cross itself, right? So an example of something that wouldn't be simple would be if it crossed itself like over here and then came back, right? And the last thing that is quite important here is a simply connected. So you have polygonally path connected, which I described here. So this set here is polygonally path connected. A simply polygonally connected set is one where you can basically create that closed path without like having any holes or anything, right? So example would be where if you had this, right? This wouldn't be this would not be simply connected because of the fact that it has a hole. So you wouldn't be able to draw I mean you'll be able to go from here to here, right? But because of the fact that you can't do this, like you can't go over that hole, it means that it's not simply polygonally path connected. Okay. Why does it keep going to that? Oh. Yep. Okay, yeah, so let's do some examples. I chuck this over here. So in general with these questions, right, I guess the best idea is to just start by drawing it. So the first one here, the first set here is a basically a circle with modulus less than 4, right? So what would that look like on the eigenplane? It would look like something like this. Where you would have 4i minus 4i, oh, that's not very visible, and minus 4 here, where this is I guess I'll write real z, and this would be mz. And well, jeez, no, I screwed up. I need to make this dotted. And so this is basically what it looks like, right? Every point in this set here has a modulus of less than 4 because we've outlined like the boundaries. So the first thing is it open? Well, it is, right? Because all these points in here, are able to make that ball. You're able to find that epsilon that makes that ball where all these points is within the set itself. And because it's open, we can also find that it's not closed because the complement, which is basically the whole complex plane minus the circle, is in fact closed, right? It's bounded because you can find basically any circle, like even the circle here, even the circle here, everything inside this set is contained within that circle, which means that it's bounded. Now, is it compact? Well, it is not compact because it's not closed. It's connected because we can draw lines between 2 points here, and so like there aren't multiple places, multiple sets, right? Or multiple like regions. And because it doesn't have any holes, it's simply connected as well. And in terms of regions, well, a region is when it's open and it contains either none, some, or all of its boundary points, right? And well, this is open, and it contains none of its boundary points, so it must be a region. And domain, I didn't specify clearly before. Well, basically, a domain is if it's an open set and it's polygonally path connected, right? So in this case, it is open and it is connected, which means that it must be a domain. Okay, I'll probably just use the same diagram. Yeah. Okay, cool. So let's move on to number 2 now. Number 2 is basically all of the points contained within the circle, including its boundary. And because these are actually boundary points and not all of these points are interior points, it's not open, and it's in fact closed, right? And like set 1, it's also bounded because we can find a circle, say we can find a circle like this, where all of its points are contained within that circle. And so that's why it's unbounded. And because it's closed and bounded, it's also compact. And I mean, very similar to 1, right? So it's also connected, and it's also simply connected for the same reasons. But in terms of, I guess it is a region because within at least this part, right? This is an open set containing all of its boundary points. And so because of that property, it is a region. But unfortunately, it's not a domain because it's not open, right? Okay, I guess a more spicier question is number 3. We just have 1 point. So let's, I'll just get rid of this. Okay. Let's consider a point, right? A point P. Is it open? Is it closed? Well, it's actually closed because the complement of the set is open. Let's think about the complement for a second. Well, the complement is the entire complex plane minus this 1 point here, right? This is an open point. And because all these points are interior points, like you can put a point here, and you can quite clearly find an epsilon where all the points inside this ball is inside the whole set. It's open, right? Because this is not actually a point inside the set. And so if you get like even infinitesimally close to it, right, you can still find an epsilon where all of the points inside that ball is inside the set. So that's why it would be open. Okay. What else? What are we up to? Bounded. Well, I'll draw the actual set. So it's this, right? And I mean, quite clearly, you can see that it's bounded, right? All you need is any ball that's larger than 1 point, and you have that specific point, or the entire set, right, is contained within that ball. Okay, so that's why it's bounded. Okay, connected, right? Well, it is actually connected because for a set to be connected, you need 2 points, right? And basically, it's like if these 2 points are able to connect to each other, where every point is within the set, then it's connected. Well, in this case, we don't have 2 points, and so I guess this is called like a vacuous truth, where because something can't happen, right? it's going to always be true. So in this case, it is going to be connected because we don't have enough points to sort of tell, right? And that translates over to simply connected as well. It's also simply connected. And because it's not open, it's not a region or a domain. Okay. Yeah. That's question number 3. Let's speed through question number 4. So pretty similar to before. But instead now we have a open circle with radius 1 and also another open circle with radius 4. It's not to scale. Okay, and this is real Z, and this is MZ. And so what we're looking at is just here, right? Okay, well, is it open? Yes, because every point in here is interior point, and as a result, it's also not closed. Is it bounded? Yes, because you can find that this can be placed inside any, I guess, ball, right? And it's contained within that ball. And it's not closed, so that means it can't be compact. Is it connected? Well, if I were to place one point here and I put another point here, I'd be able to connect it using polygonal paths. Polygonal paths. Nice. Yeah. Okay. But is it simply connected? In fact, it's not, right? Because as we sort of briefly described before, it's got that hole, right? Where if you want to connect these 2 points, you'd have to go over that hole, and these points aren't within that set itself. And so that's why it's not simply connected. Well, is it a region? Well, yeah, it is, because it contains it's an open set, and it contains none of its boundary points. And is it a domain? Well, it is an open set, and it is polygonal path connected, as we said before. And so that, in fact, it is a domain. And then let's do quickly the last one, which is just, I'll just get rid of, what about just pretend the circle's not there? Yeah, okay. Yeah, so the modulus is larger than 4, which means that it's a set of all points outside of this circle here. And is it open? Well, it is open because if you think about the like all these it contains like all these points are interior points, right? Because this is like an open boundary. Also, you can think about it as the complement would be the modulus is less than or equal to 4, so this would be set 2, which was in fact closed. Is it bounded? And I guess, yeah, so this is the difference between this question and all the other questions. This is in fact not bounded because it contains a whole complex plane, right? Minus set 5. Bounded, compact. It's not closed, right? So that means it can't be compact. Is it connected? Yes, it is, because basically if I get 2 points, I can connect them. But it's not simply connected because we have this hole in the middle. It's open. Is it a region? Well, it contains none of its boundary points, so that means it is a region. And as for domain, it is also a domain because it's open and it is connected. Okay. So those are those kind of I guess simpler questions that you might get during the exam. Acrobat. Yeah, so these are the solutions, which will be in the slides that we will release later. Okay, let's talk about functions now. Well, functions, I guess in the complex field, they're not too different from the real field, which is a good thing, right? Like we have many things that carry over, such as the codomain, range. And we also have an image and pre-image, which are a bit different to the range in the fact that, say we had a set S, right? And we were looking at the set of all function values including an f of S. well, this will be the image, right? Because it's only like the function value of a subset. And that subset S would be known as the pre-image, which is a subset of the domain. And another thing that I guess complex analysis adds is these new types of functions. So you have like the modulus function, the arc function, as well as the conjugate function. And I guess one of the more interesting parts of the complex functions is the fractional linear transformation, which is basically any function in this form. So az plus b over cz plus d, where a, b, c, d are all complex, and ad minus bc is not equal to 0. Well, I guess we sort of had to think about why this is not how it is, right? Why ad minus bc is not equal to 0. And the reason why is that if you were to represent this as a matrix of like a, b, and c, d, this would be the discriminant, right? And if the discriminant were to be 0, then you'd have that fz, az plus b would be a, what do you call it? A scalar multiple of cz plus d, which would just turn the whole thing into a constant, which is not, which is like basically trivial, right? It's not something that we necessarily care about. And the main theorem that arises and will help a lot when you're doing questions is this theorem. So if f is a FLT, like this above, and z varies on a line or on a circle, then f of z will also vary on a line or a circle, which I guess is pretty useful. So I guess this sort of arises from this question: what happens when z approaches minus d on c? Well, let's take a look. So I will chuck this over here, just for reference. So if z approaches minus d on c, right, then the denominator, cz plus d, would approach 0. And if this were to approach 0, then f of z would approach infinity, right? And because it's like approaching infinity, that means f of z must be unbounded. And because of this theorem above, this useful theorem, we find out that if it's unbounded, then that means that all these function values must be on a line, right? Because if it was on a circle, then it would be bounded, right? And so we can sort of use this to give us an idea of what the image of a function is, under an FLT. Okay, so let's do an example. This one's spicy. So the first check that you generally do is checking if it's bounded or not, just to figure out whether it's circle or line, which is sort of sometimes it really helps, like in terms of like if you find out that it's a line, and all you need to do is find 2 points, and you're able to find that line, the equation of that line. But otherwise, it can be like a verifier, like that verifies I guess your result. So consider the fractional linear transformation Tz is equal to z over z plus 2. Find the image of the circle C, where you basically have this circle, right? Okay, let's start off with thinking about T of z. Yeah. So when does the denominator equal to 0? When does it become unbounded? Well, it becomes unbounded when when z plus 2 is equal to 0, i.e. when z is equal to minus 2. And what we need to check is this point inside the circle? Well, quite clearly it's not, because if we do sub in z equals to minus 2, we get minus 2 minus 1 is equal to, well, the modulus of minus 3, which is just 3, which is not equal to 1. And so it's not a part of the circle, which is a good thing, because we know that the circle always maps onto a line or a circle, but in this case it only maps onto a circle because of the fact that we had that theorem before that told us that, and it's like, and minus 2 is not contained within that circle. Okay. Okay, so I guess generally with these questions, what you could do is brute force it. So what I usually do is let w equal to z over z plus 2, and then try to find z in terms of w, like you rearrange it, and then you sub it back in, to this equation here. And then you sometimes have to use Cartesian form to just like get everything out, and eventually you get to a equation which is a circle. But I'll do something a bit less intuitive, but like some of you guys might be able to get this during the exam. So we'll start off with z minus 1 is equal to 1. And if we were to square both sides, we get z minus 1 squared, which is equal to, as we saw in the results before, the complex number of z minus 1 times by its conjugate, which is this, but like the conjugate of a real number is just itself, so it's just this, which equals to 1 squared, which is also just 1. And if we were to expand this, we get z conjugate minus z conjugate plus 1. And if we were to do some simplification, this turns into the mod of z squared, get rid of this 1, and this is just z plus z conjugate on the other side. So that would be z conjugate squared equals to z plus z conjugate. And this is a useful result that we're going to use a bit later, okay? I can get rid of this. Ooh. Okay. Now let's consider t of z. Well, t of z, use a different color, let's use white. T of z is equal to z over z plus 2. And let's try multiplying top and bottom by the conjugate of z plus 2, which is z plus 2 over z plus 2 module squared. Because of that result I was talking about earlier, that where you have z times z conjugate equals to that, right? Yeah, and so when you expand this, you get z conjugate plus 2z over z plus 2 squared, which equals to z squared plus 2z z plus 2 all squared. Yeah, okay, so I guess this is not necessarily intuitive, but one of the things you could do here is to take the real part of this. So real of t of z, which equal to everything over z plus 2 all squared, because of the fact that this is real already. It would be this as well, because this is real. And the real part of this. Well, what would be the real part of that? It would be, I guess if you made a Cartesian form, it would be 2x, right? But in order to express that in terms of z itself, it would just be z plus z conjugate, right? Because when you plus a complex number to its conjugate, you get 2 times the real part. And so now we can use this result that we had before, this result here, by changing this z plus z conjugate into just 2 of z squared over z plus 2 squared. And this is actually really nice, because if we look back to our original question, t of z, that's actually the modulus of t of z. Yeah, just, wait, is it squared? Yes, it is. Yeah. So that's equal to the mod of t of z squared. And if we were to, I guess, express t of z as u plus vi, we get that from this, right? U equals to the modulus of t of z, which is just crap. There's a 2 here. 2 of u squared plus, I'll just stick with the same color. 2 of u squared plus v squared. And from there, you can just like sort of work out that like you just need to do some completing the square, and you eventually get to something like this. U minus 1/4 squared plus v squared is equal to 1 over 16. And so as a result, you get a circle with center 1 over 4 plus just 1 over 4, right? And so this would be center, and the radius would also be 1 over 4. Okay. Yeah. Okay. Let's jump back into the stuff. That's the solution if anyone wants to look at that. Yeah, so another part of this functions section of complex analysis is estimating the size of functions. And so I guess we're sort of running short on time, but this is an example that was inside, I guess, the notes. And really the idea behind trying to estimate the size of functions is to just use the original few inequalities that I was talking about earlier, right? I'll jump back to them real quick. These ones, right? These ones are really useful, and if you just consider them thoroughly, you should be able to solve most of the questions that ask you to find the size of a function. Okay. And now we're on to limits and differentiability. The thing about limits and differentiability in the complex plane is, again, it's pretty similar to real analysis. Like, it's not like everything's going to be completely different, but there are like obviously a few things that are definitely different. So I guess this is stuff that is shared by real numbers. So a limit is said to not exist if the function attains different values along different paths, right? Basically, pretty simple, right? If you have two values at a limit, then obviously you don't have a clearly defined limit, and the limit wouldn't exist. A limit is said to exist, that is, there's a unique L in the complex numbers with the limit of z approaching z0, f of z equals to L if the following statement holds true. For every epsilon larger than 0, there's a delta larger than 0 such that if the distance between z and z0 is less than delta, then the distance between the function value and L is less than epsilon. And so I guess this is what you would use in a proof, right? But basically what it just means is that f of z gets close to L whenever z gets close to z0, right? Basically like the nice idea of a limit, right? And so let's do a couple examples. Let's start off with this one. Prove that this limit is here. Okay. I'll probably need to screenshot this as well. So what I would usually do, because I don't really remember these proofs straight up, is try to like match everything, right? So there is a unique L. So in this case, unique 2i, right? Because that's your L. That's the thing that your limit approaches, such that lim z approaches 1 plus I z squared, that's your function, is equal to 2i if you have an epsilon larger than 0. Where it's for every epsilon, so for all epsilon. So let me just double check that I'm not being stupid. Okay, it's still working. All good. Yeah, so for all epsilon larger than 0, there was a delta larger than 0, such that, so there's a delta larger than 0, such that 0, and we don't have z0, right? It's like it's 1 plus 2i, 1 plus I. Oh, I should probably not use red. I'll just write this line in red. You can find a delta for that. And this implies that z squared minus L, which is 2i, is less than epsilon. Okay. So basically our goal is to find a delta, right? And we usually want to do this through backwards reasoning. So we'll start off with this stuff here. We want to use this in a way that we can connect it with this, and so that we can connect basically delta and epsilon together, and then we can find delta in terms of epsilon, right? So that way we always have a delta for each epsilon, so that this remains true. Okay, so let's have a look at z squared. Actually, I might use white. It's a bit like easy to read. Right, let me just, okay, never mind. Let's just double check that the stream is working. Yeah, so z squared minus 2i. Well, I guess it's not necessarily intuitive but we want to try to get this into this. So we can't really like square root anything, right? Because that would sort of affect this. So another way you can sort of try to get this like linear thing is by using the difference of two squares. And I guess it's not necessarily common knowledge, but you can find that the square root of 2i is 1 plus I, right? 1 plus I. And this is pretty useful, right? Because you can literally see there's a 1 plus I over here. So z squared minus 2i is equal to the difference of the two squares in terms of where a is z and b is 1 plus I. So z minus 1 plus I, z plus 1 plus I. And remember that we want to twist it to this, right? This chunk here. And so to do that, we want to express this in terms of z minus 1 plus I as well. So we can write this as z plus minus 1 plus I, z minus 1 plus I, and we would have to compensate by adding 2 plus 2i. Okay? Yeah. Oh. And so, okay. This comes to a bit of a tricky bit. So I'm just gonna let this be A and let this be B, right? I'll show you why later. So we can express this as A plus B, right? And because of triangle inequality, we know that this is less than or equal to A plus B, right? This is another instance where the triangle inequality or any inequalities are definitely useful, especially when you have like modulus, right? Okay, and so we get that it's less than or equal to A plus B, and what's A and what's B, right? So A is Z minus 1 plus I, plus the modulus of 2 plus 2i, which is less than delta, because remember this, right? Remember this, plus the modulus of this, which is 2 root 2, okay? And so what that comes down to is this is actually less than delta times by delta plus 2 root 2. Okay? And the goal for this is to be less than epsilon. Okay? And so what we need to do is basically we need to solve delta times by delta plus 2 root 2 is this an epsilon. And this would be a quadratic equation, right? And I'll just jump back to the slides here. Why am I here? Oh, okay. Yeah, so you would solve this and you take the positive solution. And now that you're able to find and connect delta and epsilon, right? And because we did backwards reasoning, you would have to like sort of rewrite it backwards by like basically just considering the possible delta, right? Considering this possible delta. And because it works, and you're able to find that delta for every epsilon, then this limit holds true. Yeah. Okay. Let's jump back to the second question. Why does this limit not exist? Well, like we expressed before, we can find that a limit does not exist if basically we get two different values for two different like branches, right? When we're approaching whatever value we want to approach. So let's consider two branches, right? The first branch, let's see, would be z equals to iy, where y is, well, probably shouldn't put an arrow there, I should put a line, where y is approaching 0, right? Because this would still approach 0, but what would the value of iy be? Well, it would be, well, the real part of it is just 0, and it will be 0 over iy, which would just be 0. Even if y approaches 0, this 0 still like dominates it, so it becomes 0. But what about if you just consider z equals x, where x is approaching 0? Well, you get that the real part, which is x, over z, which is just x, which equals to 1. And so because these are two different values, right? I'll do in red. These are two different values for the same limit, right? Same limits, right? Well, not really the same limit, but like they both approach 0. Because they're two different values, that means the limit doesn't exist. And so that's the main, I guess, method you're going to be using to tell if a limit exists. Just double check that nothing's coming up. yeah, so those are just the solutions. Yeah, so the same sort of limit and properties of relationships still exist. Adding and subtracting, multiplying and dividing, right? And so now we come down to the definition of a continuous function, which is basically the same thing. So we have the same proof, same definition, and we have similar ideas behind the sum and the product, as well as the quotient. Yeah. And again, yeah, differentiability is pretty similar, but sometimes it is hard to find whether a complex function is differentiable. So we have to do other stuff, right? So I'll just quickly go over this though. The function values get close to each other quicker than the inputs get close to each other. And a function is differentiable if the following limit exists. And this is like very similar to first principles, right? A good note, differentiability implies continuity. And differentiation rules from real numbers apply as usual. Okay, so normally if you wanted to find if a function was differentiable, you would use this first principles, but this can be pretty tedious sometimes. So one of the nice, I guess, theorems that we have in complex analysis is the Cauchy-Riemann equations, right? And basically, if you look at the proof, you're able to use first principles to prove why the Cauchy-Riemann equations. But right now, we'll just focus on how to use it, right? The CREs state that a function, f of x plus iy, in terms of this form, like where the real and imaginary are separated, is differentiable at an interior point at z equals to a, which is included in the domain of f, if and only if the partial derivatives of u, v all exist and are continuous, and basically these are satisfied. A nice way of remembering it is like u and x are always the first ones, like the real parts, right? And v and y are also the imaginary parts. And so this one would always be positive. And then all you need to do is you need to swap it around for the second equation. And you also have to add a negative at the end. Okay? And also, it's also really nice because we can find the derivative, which is just the partial derivative of u with respect to x, and the partial derivative of v with respect to x as the imaginary part. Okay, so let's move on to some examples. I probably won't be doing all of them. I'll just do the first one, and I'll give you some clues for the last two. Okay. Where are these functions differentiable? Well, I guess the first thing that we have to do is find out, like, is it differentiable or not, right? Or where, basically where, right? So, we are only really able to use the Cauchy-Riemann equations if we were to separate it into x and y, like those imaginary and real parts. So what we would do first of all is find what f of z is. Well, actually, find what f of x plus iy is, which is equal to x plus iy times by x squared plus y squared, because that's the modulus. And this will be equal to x cubed plus xy squared. Sorry, just closing my room door. X cubed plus y squared. Yeah, plus oops. Well, the imaginary part is y times x squared. So x squared y plus y cubed. Coolio. So that's your u and that's your v. And basically we want to test if du over dx, well, the partial derivatives, right, is equal to the partial derivative of y with respect to with v, right? And so let's just try to do this by inflection. Let's differentiate this in terms of x. We just get 3x squared plus y squared. 3x squared plus y squared. And let's do this by inspection as well. So, no, I messed up. So that should be a v. I always get this messed up. So it should be v on the top and y on the bottom. So differentiate this in terms of y. So x squared and 3y cubed. X squared plus 3y cubed. And so I guess we'll do this first. So it's only differentiable if this is satisfied. But when is it satisfied? If you simplify everything, we get 2x squared. Like we get rid of this and we get one of this. Get rid of this. Go on with this. 2y squared. And this is when we're x equals to plus minus y. Okay? But that's only one half of it, I guess, right? Because we still have the other equation that we have to satisfy. I'll still write it in white. So remember that we swapped the two. So partial derivative of u with respect to y is equal to the negative version of v. Oh, it's not v. V with respect to x. Okay. Doing this by inspection again really quickly. We get that du on. So this is just gotten rid of. We get 2xy, and on the side we also get 2xy. And we see that this only actually works if x and y is equal to 0, right? Yeah. So we get rid of the 2's. Basically, we have 2xy. Yeah, you move this over, so 2xy is equal to 0. It only works if xy is equal to 0. So at least one of them have to be 0, right? And because at least one of them have to be 0, that means the other one also has to be 0 because of this rule here. So we find that it's only differentiable at the point where, basically at the point 0, right? Only diffable point. Okay. So you would basically follow the same outline as the first question for the last two, right? You'd be doing, you'd basically just use these Cauchy-Riemann equations because they're so good, right? So that, yeah, those are solutions if you'd like. Okay, let's talk about holomorphicness now. Well, a function is said to be holomorphic if the function is differentiable in some neighborhood of A, and a function is holomorphic everywhere. That is holomorphic everywhere is called entire. So basically what it's trying to say is it has to be an open set, right? A function can only ever be holomorphic on an open set. So if a function is differentiable on a closed set, it's not holomorphic. So basically holomorphic just means differentiable and on an open set. Yeah. And now we have harmonic functions. So let D be a domain in R3. A function of two variables u is harmonic if it satisfies the places equation, which is just like this equation here. So the second partial derivative of u with respect to x, and the second partial derivative of u with respect to y, right? And all the first and second partial derivatives have to be continuous. And we know that the harmonic conjugate of u is going to be v, so that the Cauchy-Riemann equations are satisfied. So I'll show this in the last example. Yeah, this is just an important note. I guess, yeah, so these are the properties that are relevant to harmonic functions. So minus u is a harmonic conjugate of v, and I guess all the stuff you can look over in your own time. I just want to go through the example right now because we only have so much time left. Okay, let's look at this one. Yeah. Oh yeah. So if you want any hints for the second part and third part, you can always just look a little bit at the solution. Obviously, don't try to look at the whole thing, but the solutions here are pretty summarized. Yeah, like that can contain every piece of detail. Okay, so show that cos x cos y is harmonic, and find its harmonic conjugate. Okay, so the first thing that we need to check if it's harmonic. Well, we know that cos and cos itself are continuous, so we can agree that they're continuous because like we've proved it using the power series, and also like that means that their first and second partial derivatives with respect to x and y will be continuous. So let's just check the Laplace's equation. So partial derivative of u with respect to x is just minus sine x cos y. And if we diff that again with respect to x, we get minus cos x cos y. And similarly, if we take the same thing and we diff it by y, we get cos x sine y. And if we diff this again, we get over cos x cos y. And we can see that if we do, I'll zoom out a little bit. If we do, let's use green. If we do Laplace's equation, so yep, we get cos x. Actually, we'll do this one first. Minus cos x cos y plus cos x cos y, and that's just equal to 0 because these cancel each other out. And so it does satisfy Laplace's equation, and it is harmonic. Okay, I will make this a bit smaller. Didn't get this. Whatever. Okay, I'll just leave this huge. Okay, and find its harmonic conjugate. So how do we find its harmonic conjugate? Well, it has to satisfy this Cauchy-Riemann equations, right? So basically it has to satisfy positive, we'll just write them out again real quick, equals to, and this one equals to negative v on dx. Okay, well we already figured out this, right? So we have that minus sine x cos y is equal to dv on dy. And so what we can do from here is just integrate both sides. So we can find that v is equal to, when you integrate this, you get minus sine x, with respect to y, by the way, sine x. And you can treat x as a constant, sine y. But obviously you actually still need a constant. So, and the constant would be in terms of x, okay? So plus c of x. And we also know du and dy, which is over here, cos x sine y. So cos, I'll do a different color, cos x sine y. I think I said sine y. I meant sine y. Is equal to minus basically this, right? And so we can actually just get this. We want this to be satisfied as well, right? And so, I mean, this already satisfies this. So we need this to be satisfy this as well. So what that means is we need to like diff it first. So we can take the partial derivative with respect to x. And we get that with respect to x, it would be minus cos x sine y and plus c dash x. Okay, and if I sub this in, we get cos x sine y is equal to minus this. So minus cos x sine y plus c dash x. And I mean, this turns positive because of the double negative, right? And so these two just cancel out, and we get that c dash, or minus c dash x, doesn't really matter, is equal to 0. And so that means c of x must just equal to a constant. So let's let it be c. And so v must equal to what we had. So minus sine x sine y plus c, where c is c. And then so you're did I ask you for the whole function? Yeah, no, it's just asking for the harmonic conjugate. So the whole I guess function would be f of f of z, x plus iy, or just z, that's fine, equals to u plus iv, where just u is what we had above, well, what they gave to us, right? Cos x cos y. This is just if they ask you for the whole function. And it would be I times by this. And importantly, that it's I times by c as well. Another way you could sort of do these questions is by inspection. So I guess over here, it's not too hard to find, like if you have a good understanding of trig and hyperbolic trig, you'll probably find what the harmonic conjugate or like the whole function, like f, would be. But apart from that, if you can't, I guess, inspect it out straight away, you can always just bash this out like I did. So its general idea is obviously proves harmonic by using the properties of like continuous functions to verify that the first and second partial derivatives are continuous. And then after, you have to get to this bit where you just use these two Cauchy-Riemann equations, sub it in, integrate it to find b, but don't forget you have a constant, and then you use the second equation to find that constant, and then you're able to find the harmonic conjugate. Yep. These are just the solutions. Yeah, so I hope you guys enjoyed this so far. I'm going to hand it off to Wendy now to continue the rest of the, I guess, revision seminar. Have fun.
What up? I'm just gonna assume my audio is coming through until someone points out otherwise. All right, I'm Wendy. I am here to present the second half of this revision seminar. I'm covering going from exponential up to Cauchy-Goursat. Hi there, I blew up your house. And Raymond will be covering everything from Cauchy integral onwards tomorrow. So, he will single-handedly save you from eternal damnation from that half. But going over today, starting with a wonderful exponential function, we have the lovely definition, which you should be suspiciously familiar of. It's just the usual Taylor series of exponential, but it works for complex as well. So good beans. You don't have much else to go on, much further to go from there after real. We got some properties. The first one, hopefully you're pretty familiar with by this point, thanks to the whole complex number Euler form thing. Your e to the power of x plus iy. If you forget, you can, of course, just split that up a bit. And there, you can see your e to the power of x in front. And your e to the power of iy would give you the other cosine y plus I sine y. And the second one, pretty important to remember because it's, one of those things that differentiates a bit from the usual real exponential. With the complex one, it actually becomes periodic, thanks to the whole inclusion of cosine and sine. So every 2 pi ik, so, just basically every multiple of that 2 pi I, when you add it to your z, you just get the same thing back. So that's pretty fun. Nice little differentiation. Can't use that word anymore these days. Nice distinguishing thing from the real. Now we have, I just shoved all these properties on a slide because hopefully most of these you should somewhat vibe with already. Doesn't really need to be pointed out as much, like the first one, right? Hopefully that just kind of comes to you at this point. E to the power of 0 is 1. A lot of these you can see have their own real counterpart. A lot of these don't change. So e to the power of z plus w it still splits pretty nicely. It's not a lot maybe to really point out here. The derivative of your exponential is still back to your exponential. So that's a great thing. But yeah, you can just zoom over these properties in your own time. There's not a lot to point out there. The hyperbolic cosine and sine functions, same deal. With like the real version of them, it all looks pretty similar. We got the power series definitions next to them. But yeah, just more importantly, memorize those bits. And of course, these are some really lovely properties, which I believe were a bit more critical to point out just because you use them a bit more. But yeah, you have cosine of z plus w can expand into this, and the sine of z plus w. Worth pointing out, because there is a difference from like, if you think about the cosine of z plus w, the sign in the middle would have been negative, but it's positive here, so just be a bit wary. You know, hyperbolic isn't, of course, the exact same as the cosine and sine. Their cosine differentiates to sine, and sine differentiates to cosine, so no negatives involved in the derivatives either. So hyperbolic's got a leg up there. And even more properties. These ones should be relatively all right because they look pretty similar to their like does that say hyperbolic? Yeah. So yeah, it's pretty similar to the usual sine and cosine. Just this one down here, be a bit wary. It's not cosine squared plus sine squared is 1. It's cosine squared minus sine squared is 1. So never be caught out by that. Will you be able to access this recorded session again? Thanks, Felix. Yeah, you take care of the chat. You back me up. But yeah, same deal as the other one. Most of those properties are pretty similar to the real thing. We have the trigonometric functions, your cosine and sine, defined by these. If you ever find yourself forgetting them, just realize that they came from the age-old property of you add conjugates and you get twice of the real part. So, you know, adding the e to the power of iz and e to the power of negative iz, you would have just gone 2 cosine z. So there's a way to remember those complex cosine and sine functions. And also these properties are worth pointing out just because these ones are a bit, you know, it involves a bit of work if you haven't already memorized them. It's not that bad if you ever like mind blank and forget them. You can easily, like sine iz, you could sub in iz into the sine definition, figure out its version in terms of sine, but these ones are maybe worth just memorizing, and since it's open book these days, maybe worth just having in front of you. So yeah, whenever you have an iz for your sines, cosines, your sines, cosines, you can just translate them into the other version, and with just no more iz around. It's pretty fancy. These properties of the complex cosine and sine, you should be pretty familiar with them. They're pretty much the same. They are the same as the real sine and cosine. So look at this, observe this, take this in, move on. Not really anything to point out there. Now we get into, you know, the real cool things, the logarithm. So the complex logarithm, just things start happening. Let's start with the principal branch. So the principal branch, you can see got a little capital L there for that principal. It's equal to ln of the modulus of z plus I times the principal argument of z. That's also hence the capital A hanging around. That's not for fun. That is the principal argument. The principal argument is the one you would have vibed with the most back in the day and these days, I suppose. It takes the values from negative pi to pi. Negative pi is excluded. And your principal branch of the log will be differentiable on all of the complex numbers except for that negative real axis. So going all the real values from negative infinite up to the 0, including that 0 point, just not all those points, your log won't be differentiable on them. So that's pretty important to point out there. You just gotta take that in, memorize that definition of the principal branch of the logarithm. We'll do a bit of practice, you know, with actually figuring it out. The multi-valued logarithm, you can see, no longer has that any of those capital letters, so that's the multi-value, just the usual log. Definition, pretty similar. It's just that argument at the back there is also the multi-value argument. So you can see it would be that multi-valued argument. It is equal to like the principal argument, but you can add multiples of 2 pi. So that k can represent any integer there. And k can go negative, so you know you could also subtract multiples of 2 pi. So yeah, just be really careful about that difference between the multi-valued and the principal branch. Also, the principal branch is technically just one of the cases of the many branches of logarithms you can take. So if you compare your multi-valued logarithm, that just covers all your bases. If we just pick out a branch, a particular log theta branch, its restriction, like how you know what value it's going to become, the argument z is restricted going from theta to theta plus 2 pi, excluding the theta. So whatever that log theta is, that theta isn't included in your argument, and it is known as the branch cut. Just whenever your argument z is equal to theta, well, it's not equal to theta, so that's why it's the branch cut there. It's not part of your log's not going to be differentiable on your branch cut. But everywhere else where it's differentiable, the derivative is just your usual 1 over z. So it will just be something like whatever that theta is. So say your theta is that, and then bam, just that line there. There's a branch cut. Your log won't be differentiable on any of that. So if you think about it in relation to your principal, see how the branch cut restricts your argument going from theta to theta plus 2 pi. Your original principal branch went from negative pi to pi. So the theta would have been negative pi in that scenario. So this is actually the particular branch log negative pi. But we do just call it the principal branch with the capital L. That's a nice convention. So its branch cut, as you can see, would have been the argument z of negative pi. And you can see that corresponds to the whole. It's not differentiable on the negative real axis. Just everything there, just illegal. Illegal moves are happening there. So you can, hopefully you can kind of picture, see how that branch cut, you can basically just kind of swivel around depending on where you decide to take the branch. That can be real helpful for questions. But you essentially just keep taking principal branch until the question demands otherwise. Like if you just need it to be differentiable in a particular area, just swivel that branch cut until you can force it to be. If that made no sense, hopefully this will clear up some issues. Defining a branch of the multi-valued log such that it's continuous at -1 and has a value of 5 pi I. So if you just, ran straight away for your usual principal branch definition, the whole capital log life where your argument goes from negative pi to pi, would have been a bit doomed just because along that argument z of negative pi is just not differentiable, so it's definitely not continuous. Definitely not continuous at -1 if the entire negative real axis is a bit illegal for you right now. So what you need to do is swivel that branch cut around a bit. It's kind of really up to you not up to you because there is a value of 5 pi I, but we're gonna swivel it to a convenient location. Usually positive real axes. I mean, if the -1 doesn't work, just go positive, go for the next easiest case. So if I just take my branch cut, bam, along the positive axis, see how suddenly at -1, everything's G, everything's good, your log works there. If it's going along the positive real axis, its usual principal argument would just be 0. But, generalizing that, it's just every multiple of 2 pi. So that your argument of z would go from 2k pi to 2k pi plus 2 pi. You just need to figure out what particular k you're looking for. And that's what thanks to the 5 pi I. Because if you just show 0 to 2 pi straight away, because you were like, oh yeah, positive real axis, argument 0, you'll run into a bit of issues. So if you evaluate log theta -1, according to the definition of just how log is defined, you would have had, probably should have put that down. I was really dedicated to putting this in one slide. You would have had the long of the modulus of -1, which you're just logging 1. It's going to go to 0, plus the I argument of your -1. My pen is destroying me. Pretend you could see the rest of me writing down argument. But yeah, the first bit's gone, modulus is 0. You have I argument of z, so that is directly log of -1. You want it to equal 5 pi I because the question told you so. So you already made a restriction on your argument of z going from 2k pi to 2k pi plus 2 pi. You're just looking for an appropriate k to get the 5 pi I to appear. So you should be able to see from this little equation here, you want argument of z to be 5 pi. So the most convenient, the best k, just choose k equals 2, man. And then your argument z goes from 4 pi to 6 pi. You can double check if you're cautious. The argument of z is 4 pi, does correspond to the positive real axis. So you're still good. Your branch cut's still along that positive axis. And now that you've chosen the argument, You can see pretty clearly what that theta will be because it's just whatever's, down there, whatever's excluded. So your theta is 4 pi. Whoa, you didn't see me erase, just completely cross that out. So yeah, you've defined your thingy, your branch, theta is 4 pi. Now we can actually evaluate log theta of negative I. So this is now your beautiful branch definition. When you evaluate log 4 pi, log of negative I in that branch 4 pi, log of modulus of negative I, that would just be log of 1, so it heads to 0 again. You have your usual principal argument of negative I, which would have been negative pi on 2. But as we've, figured out at this point, your argument of z needs to be between 4 pi to 6 pi. So we're just going to keep adding multiples of 2 pi until we get there. So in this case, you just need to add 6 pi. And then you'll be in 11 pi on 2, which fits nicely into your argument of z restriction. And you get 11 pi on 2, according to the choice that you've made. Yep, so there's choosing a branch of your logarithm. To be fair, that is it's a pretty funky question, just because we tend to use principal branch. Your differentiability of your log, remember differentiable everywhere except on your branch cut. For this question, with the principal log, it's not differentiable on that negative real axis. So 2iz minus 1 can't be any of those negative real numbers. Now you just got to rearrange it until your z's actually the subject. So add a little 1 over here, divide by that 2i, so z's actually the subject, multiply that I to numerator and denominator, make it look nicer. And if your lambda covers all the values, all the negative real values, then ultimately your z's just going to cover from negative I on 2 and then upwards. So what that would look like would be here's negative I on 2, everything there. Yeah, not differentiable everywhere along that. Now, of course, pointing out a beautiful final question. So, finding all complex numbers z such that sine of z is equal to 2i, because, previous examples were all log. Now it's time to bring it back into the good old trig functions. So to solve these questions, pretty much the standard method, you just firstly use the definition. So whatever it was defined at. So sine z is defined as this. So just insert it in. What you're going to do is you're going to let that e to the power of iz be w. If this was something like shine, like if that was e to the power of z, you would have just let w equal e to the power of z. So the whole point of letting w equal e to the power of iz is your equation ends up looking like this. Oh, multiply the 2i up. Ends up looking like this, which when you multiply w to it, gives you a quadratic equation. So you can actually solve for w using that legendary technique of the quadratic equation. And then you remember what you were actually trying to do. So you were trying to solve for z, solving for w, and it gets you, to a certain extent. Now remember that w is e to the power of iz. So in order to solve for iz, logs are back again. You really can't escape those logs. So remember, we're solving for e to the power of iz equals w, where w is negative 2 plus minus root 5. We're just gonna take the cases separately. You can try and combine them, do them at the same time if you wanna. But taking them separately, w is negative 2 plus root 5 first. So you're solving for iz is equal to log of negative 2 plus root 5. We are just taking the multi-valued log. We're just going to find all the solutions of z. We're not trying to restrict it off. So yeah, iz is equal to log, the multi-valued log of negative 2 plus root 5. According to the definition, that will be log of the modulus of negative 2 plus root 5. Plus the argument. Notice there's no capital letter for argument because we're just taking the multi-valued argument of negative 2 plus root 5. Modulus of negative 2 plus root 5 is just negative 2 plus root 5. It's a positive real number. And the argument, the principal argument of the, did I say negative? But the principal argument of the positive real number, negative 2 plus root 5, that's just 0. So that's where the 0 comes from. Because the argument of negative 2 plus root 5 is just 0. And then you just add a bunch of multiples of 2 pi to get the rest of your argument values. And then you simply divide an I off, because so far it's just iz. To actually get z to be the answer, you have to divide an I off to everything. And that's how you get this lovely solution over here for z. repeat the process for -2 minus root 5 for w, pretty much the same. The difference is, of course, okay, so like over here, because this is now a negative real number, when you take the modulus of it, it's 2 plus root 5. You wouldn't be writing down -2 minus root 5. And because it's a negative real number, its principal argument is not 0, its principal argument is pi. So, but other than that, working out pretty similar. You still add multiples of 2k pi, and you still divide off I in that final line of working, just to get whatever z is. And these types of questions always work out like this. So, if you see it, you thank them. For, it'll look like they want you to solve for cosine equals something or cosine equals something, but it's always this method. Defining the complex powers. So, powers are defined, once again, starting with the principal branch. You have this z to the power of alpha. It's a nice little power there. The principal branch of it will simply be the exponential of alpha times principal branch of log. And the multi-value function you can see pretty similar, but the principal branch of log is just replaced by the multi-valued log, which hopefully makes sense. Multi-valued power, multi-valued log. And you can see, you can actually relate them to each other pretty easily. Since remember, the multi-valued argument, the only difference to the principal argument was that it could have gotten a bunch of extra 2k pi. So that's where this extra term just pops out from. So yeah, that's the only difference to the principal value. Go ahead, memorize that, take this into your soul. And then we try out an example because, that's the best way to learn. So maybe I should note that down. So the principal value of z to the power of alpha is exponential alpha principal value of log. Yeah. So when we evaluate negative I to the power of 2i, it will be the exponential of, so the 2i you can see comes down, and then you log, well, it's not the principal value here, so it's not the principal log, it's just the multi-valued log of negative I. Then you use the definition of log, so once again, long modulus of negative I, plus I times the principal argument of negative I, which is negative pi on 2, plus multiples of 2 pi. Your long of, well, the modulus of negative I is just 1. So long 1 is 0, so that whole thing is just gone, ta-ta. And the second bit over there, the 2i times I is actually just negative 2, and then you can expand the brackets to give you pi minus 4k pi, where k is an integer. And if you've done it, pretty carefully, when you figure out the principal value, remember the only difference was the principal value gifted you this extra term over here. The principal argument is right next to it, the negative pi on 2. So when you write down the principal value of the complex power, if you've done your working well enough, you just have to remove that term, and you don't have to redo your working or anything. So yeah, there's the finding complex powers, and hopefully that clears up a bit more of the issues of the difference between principal value and just finding a usual multi-value. Complex power again, but a bit more unusual. So we start off pretty chill. You do the usual, bring the power down. Because it's principal value, you got the principal log, and then things get weirder. Because when you're trying to evaluate that limit as z approaches 0, naively, like a fool, you decide to just sub in, well, not a fool, this is correct. You try and sub in z equals 0. You end up with 0 in the denominator, and in the numerator, cosine of 0 is just 1, and then log of 1 heads to 0, at least the principal value of log heads to 0. So what you gotta do, hopefully this stirs up long forgotten memories. This is you trying to evaluate a limit of 0 on 0. We can use L'Hopital's rule to take care of everything. All you gotta do is differentiate that numerator and denominator. So differentiating z squared gives you 2z. Differentiating that log there gives you negative sine z over cosine z. If you just use a little chain rule. And that's still not enough. So keep going. So differentiate it again. Negative sine z on cosine z, remember, is just negative tan z. So it differentiates to negative sec squared. 2z differentiates to 2. And now you're good. Now when you sub in 0, you get negative half, since sec z is 1. So this one is a bit spicier, but not because of the log. It's just because of the weird limit. It's all thanks to that L'Hopital's rule trying to catch you out. But hopefully the complex power bit is still pretty good. Now, when it comes to differentiability of complex powers, you can see because of the definition of complex powers using log, it works out the same way when we were trying to figure out the differentiability of logs. So just convert this root z plus 1, just put it into its nice little log form there. Not log form, the form that involves log. So using a complex power definition, remember root z plus 1 is just z plus 1 to the power of half. So bring the half down, and then remember principal branch means principal log of z plus 1. Your z plus 1, just because of the principal branch of log, your z plus 1 doesn't exist anywhere in that negative real axis. Oh, shizzles. Anywhere in that negative real axis. So that means z itself, your function won't be analytic when z goes from negative infinite to negative 1, because that's what gives you z plus 1 going from negative infinite to 0. So that's just a little bit of a, manipulation in that final line of working. The principal branch of root z squared minus 1, where it's analytic, pretty similar working as the top one, actually. You can see it's still got, you bring the half down as that power there, principal branch of log, z squared minus 1. Z squared minus 1, again, just by how principal log is defined, that log won't be differentiable on z squared minus 1 being on the negative real axis. So that means z squared itself has to go from negative infinite to 1. So you can see how it's pretty similar to the top one over there. The only issue is now you need to actually work out what z can be. So if z squared, sorry, not what z can't be. So if z squared, if your function isn't analytic when z squared goes from negative infinite to 1, so all the negative values of z squared immediately are kind of out. So there's all your imaginary numbers since they all square to a negative. So there you go, taking care of negative infinite to 0. And then the z squared values from 0 to 1 are taken care of when z covers the real values negative 1 to 1. So your function analytic everywhere except those sections. So the differentiability of complex powers just depends on you understanding that differentiability of log pretty well. And you can see, like I said before, a lot of the time it's the principal branch of log. So the whole swiveling branch cut technique doesn't come up a lot. That was the finish of that differentiability topic. Now we move into the lovely contour integration, otherwise known as the beginning of the end, or perhaps the beginning of your true passion for this subject, starting with defining curves. So, now we're all the way back to foundations. We have a curve in complex numbers, because complex number topic. Continuous function, we're going to represent this curve by gamma. And it goes from the range of values a and b, you sub it in, and then you pop out a complex number. The initial point of the curve, which is gamma of a, and then you have the final point, which is gamma of b. So that's just what the range a to b there. A gives you initial, b goes to that final point. The range of your curve is just gamma of t, so just all the t values from a to b, sub it in, so all those values your curve covers. There's the range. Your curve will be closed, so you have your chill curve going from gamma on A to gamma on B, covering all the gamma on T values in the middle. Your curve will be closed if your gamma of A just heads back and bam, just ends up gamma A equals gamma B again. Then you have your lovely closed curve. It will be simple if gamma of S isn't equal to gamma of T when S is less than T, except for fossil, long definition. Basically, a simple curve doesn't go over itself again. So here's a curve, everything's really chill, bam, suddenly crosses itself, no longer simple. But you are allowed to, like the second one in the middle here, that's still simple. It's allowed to cross itself right at the initial and final point. But if it's simple and it manages to be closed, you can call it a nice little Jordan curve, so you don't have to write 2 words. Math. But yes, so hopefully this will clear up any issues about the classifications of simple and closed. The first one is simple because it doesn't cross itself, but it's not closed because you can see the initial and final points are different. The second one, it's closed. You can see, you don't really see where its starting point is, but just the fact that it's a closed shape, like maybe there was a starting point. You can see it met up with itself. So second curve is closed, but not simple because it crosses over itself right over here. And the third curve, simple and closed, so it's a Jordan curve. So that's pretty lovely. That was just a little classification, a bit more terminology. You have two curves. If you can have a join of those two curves, and this should be hopefully relatively, I mean, this definition looks a bit horrific, but honestly, here it is. Here's your alpha curve, and your beta curve joins up right there. Its initial point right at the final point of alpha. And then bam, you got the join of alpha and beta. So that's all that's going on here when we have this very fancy definition. And then the reverse curve, once again, definition looks a bit fancy. The gamma star there, standing for the reverse. So your curve going from A to B. And then what if your curve went from B to A? Bam, we got the reverse. So that's all that definition is. These are all very, nice formal stuff. But ultimately, it should be, hopefully, relatively intuitive going from a diagram, what these definitions are trying to say. If you haven't noticed yet, we are going to do a bunch of parametrization. So just pointing out the parametrization of lines and circles because they happen a lot. So if you have a straight line between the points Z0 and Z1, you can parametrize it just using that age-old technique of the parametric vector form of lines. So you can see you start from a point Z0, then you plus t times that vector Z1 minus Z0. That's a way to think about, how to memorize the parametrization of lines. And your t values cover 0 to 1. And you can see t equals 0 would correspond to that Z0 point, and t equals 1 goes all the way to the Z1 point. So you do get from the initial to final. Now for the circle with center Z0 and radius R, it's usually parametrized like this. So your circle has firstly Z0, so you get there, and then you just add a little R e to the power of it. And you can see they'll cover every point on your circle. You can just swivel around that t value from 0 to 2 pi, and your little radius there will cover the entire circumference of your circle as it rotates around. So t equals 0 would of course just be right down here, and then bam, 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 goes all the way. T equals 0 all the way to t equals 2 pi, and it covers your whole circle. So these are just two parametrizations, which you should hopefully be pretty familiar with. If not, just memorize them. You're going to be parametrizing lines and circles a bunch. Now, derivatives used a lot. So let's define derivatives. Mostly, you should be pretty chill with the definition of it. You got this curve gamma t. If you split it up into gamma 1t plus gamma 2t times I. So just gamma equals gamma 1 plus I gamma 2. So just the real and imaginary parts, its derivative, just differentiate the real and imaginary parts separately, and you're good. You got the derivative of gamma. Now we call this continuously differentiable if your derivative exists, and if it's continuous. It feels like kind of a bad definition of continuously differentiable, but yeah, that really is. Now this more interesting, it is smooth if it's continuously differentiable, but the derivative never equals 0 at any point. So yeah, just be a bit careful about what a smooth thing is. And it's piecewise smooth if it's a finite join of a bunch of smooth stuff. So remember the finite join thing from like the join of curves from before? You were just like putting curves, the initial point at the final point of the previous one. So remember the whole smooth, it's got to be continuously differentiable. Most of the functions you meet are just going to end up being piecewise smooth. So like all the pieces are smooth, but just right where they join, it just isn't. So like here, for example, really abruptly, bam, like look at that. It's not differentiable at that point here. But because the pieces it's made up of are continuously differentiable, we call it piecewise smooth. It's like you just put together all the good parts, pretend those middle parts didn't happen, like your grades. And anyway, looking at this function, is it smooth or is it perhaps piecewise smooth? So this curve, going from -1 to 1 in complex numbers, it's given by modulus of t plus it. Well, absolute value of t plus it. Your t only covers the values from -1 to 1. That absolute value doesn't exist at t equals 0. Hopefully you remember that derivative well enough. So your curve's not smooth because the derivative just doesn't exist at a t value within that -1 to 1 zone. But what you can do, split it by the whole usual definition of how you split up absolute value. So absolute value t, it would be t when your t covers the 0 to 1 values, and it's negative t when t covers the -1 to 0 values. And see how individually those two curves, they're both smooth. you can see both of them have derivatives that exist. So like your gamma 1, whoa, yeah, yeah, it only gets worse. Okay. So your gamma 1 dash would just be, I think my pen broke. It's not lifting. Gamma 1 dash would be 1 plus I. That's my point. And the other one would be minus 1 plus I. So derivatives all exist and they're continuously differentiable. So that means each of those pieces there are smooth. So overall, your gamma is piecewise smooth. And yeah, that'll happen quite a lot. Moving on. Also a little sidetrack into just what a curve length is. So the length of a piecewise smooth curve would simply be you integrating over that range, the a to b, and you're integrating the modulus of its derivative. So just a quick demonstration of what that means. So you've got this gamma curve hanging around, equal to r e to the power of it. T covers the values from 0 to 2m pi and some natural number out there. R is some positive. Its derivative would just be r, you can just keep it there as a constant. E to the power of it is a little chain rule. It would just become, remember exponentials differentiate to themselves again. And then you have I, just from the derivative of it. So the length of our curve, according to that wonderful formula up there, you would simply be integrating over those bunch of t values, so from 0 to 2m pi. Then you take the modulus of its derivative, which you've already worked out as derivative. Now the modulus of ri, e to the power of it, is simply r, because remember, modulus of I is 1, modulus of e to the power of it is just 1. R is just a nice little constant there. So there's its modulus. And if you're integrating just that constant, that would become r. Oh, my pen is actually permanently broken. That's really sad. Okay, so that integrates to t, and you can sub in the upper and lower bounds of 2m pi and 0 to get 2m pi minus 0, and that's how you get the 2m pi r. Ugh, need to fix that. Okay, now what a contour is, because so far we've really just been talking about curves. Don't worry, the contour is not much more of a step up. So your contour is the oriented range of a piecewise smooth curve. So we still got the piecewise smooth curve hanging around, but now it's actually got a direction, and then it becomes a contour. So that contour, it's an oriented range. And the standard orientation would just be you going around. If it's a closed curve, the standard orientation would just be running around, so the interior remains on the left. But yeah. So defining the integral of a complex valued function, it's not a lot of plot twists you would expect here. So your f, which is equal to u plus iv. When you integrate f, you can integrate the u and then add I times the integral of v. So I, you can just think of it as a constant, which we pretty much have been thinking of it as one. So not a lot of plot twists with the definition of how to integrate a complex valued function. These identities, not many plot twists, not any plot twists actually. They all have their nice little real counterparts. So you can see lambda f plus mu g, sorry, the curve is out to get me. You can split them up into two different integrals, and you can chuck the constants lambda and mu outside. When you have the second thing over here, f of h times h dash, that's of course is just reverse chain rule, still working out really well over here in complex life. That third one is just your usual integration by parts, no worries, still works in complex integration. And that final one's just a nice, lovely inequality. Still carrying over from the real integrals. So yeah, it's a nice properties to stare at, but there's no new things really to be learned from here other than, it also works for complex. So a nice little demonstration of how integration by parts still works for complex integration. You're trying to integrate t e to the power of it over that 0 to 2 pi. You can still use integration by parts over here. So you would be, you can see here, that your e to the power of it has been integrated to e to the power of it over I, because I is just another constant. And then you can see your t there gets differentiated to 1. I mean, you don't see the 1, but Oh, come on. think I need to reboot my pencil. But yeah. Yeah, so you use integration by parts on that, and I don't really have a lot of comment on that actually. It's just a demonstration of how you can use integration by parts. And you can see here that when you try and integrate your t cosine t, you don't actually have to start from scratch, thanks to the previous example where you integrated t e to the power of it. If you think about it, your t e to the power of it, just by definition of what the exponential was, your t e to the power of it is actually t cosine t plus it sine t. So your t cosine t would just be the real part of what you integrated back over here. What you integrated back over there gave you just a completely imaginary number. So the real part's 0. Yeah, that's such is life. Now keep going. Let's define what a line integral is. If you're trying to integrate f over that piecewise smooth curve gamma, we define your complex line integral as this, f of gamma times gamma dash. You can think of this, integrating from a to b. So you can think of this as just substituting in z is gamma. You can even see, so you can see z originally covering that gamma curve on the bounds, and then because you're integrating with respect to t there now, thanks to the substitution of z is gamma, now the t runs from a to b because that's what the gamma covers. Your f of z is now f of gamma, and of course you have gamma dash because substituting z, dz on dt is gamma dash. So yeah, that's, if you completely blank on what a complex line integral is, you can always just sub z is gamma and figure it out. But hopefully just memorize this definition. So this is the complex line integral. Once again, there's not really any plot twists when it comes to the properties. You can still split up integrals. You can still chuck out constants. If you're integrating along the reverse, it's just negative. So here you can see, remember alpha star is the reverse curve. It's just negative of your original curve because, you go one direction and then you go the other direction. Yeah, it's just your typical flipping the bounds. So your integral gets a negative slapped in front. And here, gamma is the join of alpha and beta. So here you have alpha and beta. And bam, you can just, if you integrate it along this whole thing makes up gamma. You can just, usual splitting up of integral, splitting up of the bounds into different integrals. So no real new properties there. So just a demonstration of how line integration works. You're trying to integrate the conjugate of z over gamma, where gamma is the straight line from 0 to 1 plus I. Based on all those definitions, you do need the parametrization. So we are parameterizing this line. So we start from 0 plus t times final point minus initial point, and t covers the values from 0 to 1. And then its derivative would simply be 1 plus I. So when we evaluate this, according to how the complex line integral is defined, the first part, so the original f of z is just the conjugate of z. So f of gamma, you would just be taking the conjugate of gamma. So if gamma is 1 plus it, you can see here how the conjugate of the 1 plus it just came out as a 1 minus it. T is just covering the real values from 0 to 1. So you don't need to worry about slapping a conjugate on top of that one. It's just the 1 plus I bit that gets into the 1 minus I conjugate. Conjugate of t just comes back to t. And of course multiplied by the derivative of gamma dash, which is 1 plus I. So there's your gamma dash getting subbed in. 1 minus I times 1 plus I is 2. And then everything falls out really lovely. Integrating 2t, that's the usual life. So that's 2 times t squared over 2. And then you can sub in your bounds. So there's your beautiful complex line integral. You can see most of it was really dedicated to just finding that parametrization. Would you look at that? Here's a final exam question with you evaluating a complex integral. And might have been a poor choice on my part now that I think about it. It's also integrating conjugate z. But this time they just gave you the parametrization. Like, here it is, gamma is t plus it squared. You didn't even need to try. T plus it squared for t going from 0 to 1. Take advantage of the gifts they have given you. So according to the definition of complex line integral, here you are, going from t is 0 to 1. And for your f of gamma, remember your f of z is z conjugate. So your f of gamma would just be the conjugate of gamma. So here's the conjugate of t plus it squared multiplied by the derivative of gamma, which is the usual life. T integrates to 1. It squared integrates to 2it. T, remember, still covering real values from 0 to 1. So when you take the conjugate of t plus it squared, it's just t minus it squared. Just treat the t there. It is a real number. Do a little expansion, and that should be a reverse power rule. So that would be t to the power 4 on 4, then you have t cubed on 3. Remember, I is just a constant, and t integrates to t squared on 2. So sub all that stuff in, and you'll get your lovely 1 plus I over 3. So that was just demonstrating how the complex line integral works out really well. Reparametrization, just a quick sidebar here. Notice how we've been parametrizing curves. You can parametrize them in different ways. Like, for example, this is a really basic one, but say you have gamma equal to t covers 0 to 1. You could cover the exact same thing by taking t plus 1, but t goes from -1 to 0. But technically, the gamma and delta here are two different parametrizations. So it's this is known formally, the reparametrization, and that's a pretty nicely formal definition, which you can just peruse. But yes, when it comes to the piecewise smooth curves, it's fine. If you have different parametrizations, you'll still end up with the same value. So that's just a good side note to if you're concerned over that, you're like, oh, I parametrize this differently. You're good, man. As long as it's the same curve, not going to affect your integral. Now this lemma over here, the ML lemma, otherwise known as the estimation lemma, it's a pretty useful one for giving nice little upper bounds. So if you're trying to integrate this f over your piecewise smooth curve gamma, its modulus is always less than or equal to m times L, where the L is the length of your curve. If your curve, for example, happens to be a circle, that'd just be the circumference. And your m is a maximizer. It's not actually, so if your curve is doing a thing, that's a terrible curve. I should have just gone for an easier one. Your curve's doing a thing, say down here. See here how technically you can see the maximum value it reaches is at that 2, but you can just like make m equal 3. Oh wait, that was a really poor choice. This was a really bad choice on my part. No wait, sorry. You didn't see that. If this was f, so the modulus of f would just be 2. You can see the maximum is 2, but there it is. I could choose 3 to be a maximizer, and it's still fine. So m just needs to be a number that's always like bigger than the modulus of f, and it's cool, it can be m. You don't need to find the actual exact maximum of whatever f is. And as you're going to come to realize, it may sound a bit weird, but at the end of the day, it's just triangle inequality. Pretty much nearly all the questions. When it comes to finding whatever capital M is, just use the triangle inequality. So an example of what I mean by that, you have the modulus of your integral of f over the curve gamma. You're given that monstrosity of whatever f is. Gamma is a circle centered at the origin with radius 3. Show that this is less than or equal to 33 pi. That should really trigger some alarm bells in your system, because that looks, the left-hand side is pretty much, that's the ML lemma right there. So what you need to do, you need to find that maximizer of the modulus of f. And now f looks a bit horrific right now. Just keep in mind that because gamma runs on that circle with radius 3, center origin, then the modulus of z is always 3. So by the beauty of triangle inequality, that top numerator there, when you modulus it, it's just going to be less than or equal to modulus of z squared plus 2. So if you're wondering where the triangle inequality is going to come to haunt you again, it's come to haunt you again. So 3 squared plus 2 is 11. There's the upper bound on your numerator. Now your denominator, if you try and use triangle inequality, it won't work out really well because you want the max value of f. So what you actually need to do is find the minimum of your, you just need to try and make your denominator greater than or equal to something. And that is, you can use the circle inequality to take care of all of that. Oh, I should have pointed that out. So you find m using triangle inequality and circle inequality. Oh, that just looks like a 0. Pretend I wrote the word circle. But yes, using circle inequality gives you a greater than or equal to instead of the less than or equal to. And once again, modulus of z is just 3. So ultimately, your denominator is greater than or equal to 2. And overall, that means the modulus of your f is less than or equal to 11 over 2. So you have a maximizer, m. You don't really care if it's not the actual maximum. It's a maximum. It's bigger than or equal to all the modulus of f values out there. Now, since your gamma is a circle, you are blessed. Its length is simply the circumference. You don't have to use the fancy length of a curve formula from back then. And then 2 pi r will give you 6 pi. So according to the ML lemma, you got 11 on 2 times 6 pi as that maximum for the modulus of the integral of f to give you 33 pi. So yeah, that's lovely. Now your contour integration, like I said before, the contour was just the oriented, it's your curve, but it's got a direction. Now defining the contour integral is pretty chill because like we said, you can reparameterize the curves any way you want and it still gives you the same value. So there's your contour integral defined. Let's keep going. Yes, what we've all been building up to, the Cauchy-Goursat theorem. So suppose a mega is a simply connected domain, which if you've been hallucinating over the past 2 hours, you may have forgotten. The simply connected domain was just a thing out there, and there's no holes chilling around, and you can take a point, get to another point. So yeah, there's your simply connected domain. Your f is holomorphic over that thing, so it's differentiable over that entire whatever, and your gamma is a closed contour in that omega. So, its initial point is its final point. Then, if all those conditions are beautifully satisfied, that's pretty damn powerful. The integral of your f just goes to head being 0. That's amazing. That's like kind of like a more special case. The general form is technically down there. Your omega is a bounded domain. So say like blah, but it's got like a bunch of, there's gamma 1, gamma 2, gamma 3. So you can see how it's made up of a bunch of contours, but you actually, as long as your f still remains holomorphic on like that entire open set containing whatever your omega is doing. So, there's your omega. As long as your f is holomorphic on that whole thing, you can still, that whole integral ends up going to 0, and you can find it just by summing up along each contour. So you can see here it's a sum along each of them. So just gamma 1, gamma 2, gamma 3, like life is still really good. It all just heads to being 0. So a quick demonstration of Cauchy-Goursat, but it's like a nice version of it. Not nice version, just a nice chill question. You have the integral of 1 over z minus 2i, integrating over gamma 1, where gamma 1's some circle centered at -1, radius root 2. Wow. So there's your nice little gamma 1. It's going anti-clockwise, so my god, it's a contour. Now, your f. Remember because that's one of the bigger restrictions of the Cauchy-Goursat. The whole f has to be holomorphic on that entire omega. Now your f is 1 over z minus 2i, so it's actually pretty fine as long as your z doesn't hit 2i, and you can see your contour very nicely avoids 2i, so you're good. F's differentiable on your contour and inside your contour, so you can just use Cauchy-Goursat theorem on it and it's equal to 0. But you can see how this can get extended, right? Like as long as your contour is chilling outside and avoiding 2i, it just keeps being 0. The Cauchy-Goursat will take care of you. Cauchy-Goursat, but it's sudden death. This example is a bit. Wait, hang on. Do I only have one thing left? I'm just going to quickly cover this concept because that's the only concept left. I'll come back for the sudden death question. But consequences of Cauchy-Goursat. To just quick side notes here, independence of contours. If your contour is same, the initial and final points, it actually ends up being the same. It's pretty nice independence of contour. And this is a pretty major one, existence of primitives. So it's all equal, but what are all these mysterious integrals equal to? They're equal to this. If you have your function f and you know it's primitive capital F, otherwise known as the antiderivative, now, pretty importantly, that little f still has to be holomorphic on all of omega. That condition's always going to come back to haunt you. And your capital F's, of course, it's going to need to be differentiable the whole way through if capital F dash is little f. But it's always equal to that primitive of that final point minus subbing in the initial point into your primitive. So yeah, you just got to check out those conditions first before you try chucking this primitive formula on them. So a quick example of the primitive, how you would use it. You have your gamma, a straight line going from 0 to 1 plus 2i, and then some parabola going from 1 plus 2i to 1 minus i. I want you to find the integral of sine 2z over gamma, and you're like, well, that's I don't really want to find the parametrizations of, lines and parabolas and whatever. You can avoid all that hard work, right? You just need to have that primitive, and everything still needs to be holomorphic. So the primitive of your sine 2z, just the usual life of integration, is negative half cosine 2z. And you thank the blessings that have been blessed for you today. The sine and cosine and whatever, they're all analytic on just all the complex. So you're good. You can use the formula. Your integral of sine 2z is simply equal to that primitive, and you sub in the final and initial point. So you don't even care that your contour made this little, segue into going to 1 plus 2i before it headed to 1 minus I. You don't even care what the curves are doing. You just know the initial point is 0 and the final point is 1 minus I, and you just sub them in to your primitive. So your primitive is negative half cosine 2z. So you sub it in and you have cosine of 2 times 1 minus I. So there's the 1 minus I being subbed in, minus cosine 0, which is just 1. And there you have it. There's your integral. Life is really good if you can use this primitive method on it. You know what? Yeah, I'll go back to because that was the final example there, but it's a bit of a branch logarithm. This one's a bit funkier. So Cauchy-Goursat, but I call this the sudden death question. So you have this integral. It looks horrific, but they do give you a nice little hint. Consider an integral of f equals 1 over z plus I all squared. I say really nice. It's a bit hard to see the connection, but we'll get there. So firstly, you consider, right, this original integral, whatever it was, it's heading, it's the entire real axis, basically, going from negative infinite to infinite. Now, you can't really do much with this, like when you just integrate along that, but what you can do instead is consider these nice little contours. So you have gamma x, gamma r, where that gamma r there is just that upper semicircle, and the gamma x is just that line between negative r and r. And you can see here that when gamma x shoots off into being infinite, that's where you get that integral negative infinite to infinite. And that top bit there, that semicircle there, is just, it's there just to give you that closed contour, so you can actually use Cauchy-Goursat. Otherwise, you can't really do anything. Cauchy-Goursat relies on that closed contour. You also need to check whether your f remains holomorphic on that whole thing, and you can see your f is 1 over z plus I all squared, and you're avoiding that cheeky negative I down here by keeping that upper semicircle. And even when your gamma x shoots off into being infinite, like your circle gets larger and larger, it's fine. You're never gonna have an issue with your f trying to be non-analytic. So your Cauchy-Goursat tells you going over those contours, so gamma r, the join of gamma r and gamma x, which we're just going to call gamma. So going over that entire semicircle thing, it's equal to 0, such as the Cauchy-Goursat life. More importantly, you want to see what happens to gamma x. So we'll get there. We need to evaluate it separately. The gamma, we need to get the gamma r and the gamma x, what both of those contour integrals are. The gamma r is a bit annoying, but, and you thought this lemma wouldn't come back. The ML lemma can actually take care of issues for you over here. So what you can do with it, your f function, remember from the question, was just that's just what the question told you. That is less than or equal to 1 over capital R minus 1 all squared. And that is just via the beauty of the circle inequality. Because remember, on the gamma R contour, your modulus of Z is simply capital R. So with your whole the Z plus I, using the power of circle inequality, you get this. Using circle inequality, because the whole denominator thing, you only use triangle for the numerator. And would you look at that? So that's how you get the less than or equal to 1 over r minus 1 squared. And, well, that's only valid for r bigger than 1 when you try and shoot some stuff out. But that's all right. We're making r going into infinite by the end of this. Now, the length of your contour there is just a semicircle, so pi r. So by the ML lemma, you have the length multiplied by that maximizer, which again, you found via either circle or triangle inequality. That's just how the ML lemma pans out. You know what that modulus of your f over the gamma r contour, you know what its max is. And when you make the r shoot off into infinite, that pi r over r minus 1 squared actually just heads off into being 0 once your r goes off into infinite. So that's real helpful for you because you're only really interested in that gamma x, right? You didn't really want that gamma r. But yeah, that goes off into being 0. So your integral must go to 0 as r goes to infinite. So life is really great. because the upper bound's 0, so the integral's got to be 0. Now, oh yes, if you've forgotten what the original question was, we are just looking for, oh, well, you can see that there it is. That's the integral we were going for. So if you now look at the other contour, so we took the semicircle, and now we look over the line. The line only goes from negative r to r over the real values. And you can see how multiplying x minus I all squared to numerator and denominator gives you something real suspiciously close to what you're actually trying to find. The only difference is what you're trying to find there. It's the real part of currently your contour integral over gamma x. So all you need to do is pick out the real part. So if you pick out the real part there, and you contour integral over the entire gamma. Remember what we proved before up here, going over gamma r, the whole thing's just 0. So it's not even, it's a non-issue. You can put it in if you want to. So there's the contribution for gamma x, and the contribution from gamma r is like a plus 0. That entire slide previously was just dedicated to this term you don't even write down when you're working. But yes, plus 0 for that gamma r. So you're left with just gamma x as life intended. And if you just take the real part, boy howdy, you can get exactly the integral you were trying to find. And all the way back here, remember what Cauchy-Goursat gifted you. Going over the integral of gamma is just 0. So this bit over here is just 0, and the real part of 0 is 0. So that's how you prove that integral ultimately is simply equal to 0. But yeah, it is that's a bit of a wild ride of a question. My God, it's 5. I never planned this correctly. Well, and there's this final question over here. The main gist of this one was because your contour, so this contour here starts from I, goes to negative I, but the restriction is it has to go over the areas where your real part of z is less than or equal to 0. So your contour can do crazy stuff, but it has to stay, it has to stay to the left of your imaginary axis. So the whole point of that weird restriction is if you try to use the primitive on your 1 over z minus 1, you can't use the principal branch of log because it's your 1 over z minus 1. It doesn't stay analytic where your contour is trying to go because it's not analytic anywhere on the negative real axis, and your contour at some point has got to cross that negative real axis if it wants to get from I to negative I and stay on the left of your imaginary axis. So the plot twist to this question was you just chose the positive real axis as the branch cut, and there's no more plot twist after that. You just need to figure out that you're going for that 0 branch cut, and then you can choose your argument appropriately, only going from 0 to 2 pi instead of negative pi to pi. But other than that, the question works out pretty similarly to the before one, where once you have the primitive, which as you can see we figured out to be log 0 z minus 1, you can sub in your final point, your initial point, and life pans out well. You just have to remember the definition of log, and your restriction on argument these days is 0 to 2 pi instead of negative pi to pi. Hence this funky thing over here where you had to add an extra 2 pi to your principal argument in order to fit your argument within the 0 to 2 pi. But yes, ultimately you can just figure that out now. So be a bit careful about trying to use primitives. It's all about where your function still remains analytic. So just be Cauchy-Goursat primitive stuff. It's all about where your function is still analytic. Sorry, machine learning lemma. That's good. But yeah, that's the end of my speed run of that life. Tomorrow, of course, you will continue with the good old Raymond, who will who will really carry you essentially, because as we all know, the final exams test the latter parts of the topic more. But hopefully this was a sort of revision of all those foundational concepts in preparation. So, hope to see you all. Well, I won't see you all. Maybe I'll come swoop by or something. Yeah. And yeah, I don't got nothing else to say really. How's it going, guys? I probably should have asked that first. Yeah, okay, I'm just gonna go end this stream. Goodbye, good luck on your beautiful. Oh, right. Sorry, is the test not open book? I mean, it's open book. I mean, like let's be serious. Let's be real serious, guys. Thank God we're still in COVID, but yeah. yeah, hasta la vista. Good luck for those finals. I'll be right there with you, crying. Not crying, I'm sorry, celebrating because we're in a math major. How could you be sad when you're in a math major? And how could you be sad when you're learning about complex numbers? Everything makes sense, right? Yes. Yeah. I've forgotten how to. I can't find myself.